Previously, to solve the parabolic PDE, we have used the explicit method to approximate the d squared t over dx squared by using this equation. And since this is a first order accuracy method, we continue to improve the accuracy by approximate this derivative to be this formula. So this is called the implicit method. And the accuracy is second order. However, for the explicit and implicit method, for the temporal difference approximation, the accuracy is still first order. So in order to improve this accuracy, an alternative implicit scheme, which is called the Nicolson method, is introduced. In order to increase the accuracy of the temporal difference approximation from first order to second order accurate. To achieve this, Nicolson method approximates the d squared t over dx squared by taking half of the explicit formula plus the implicit formula. By substituting the spatial difference approximation and also the temporal difference approximation into this formula, then you should be able to obtain this equation. By multiply delta t, this part can be cancelled and you have delta t here. Since lambda equal to k delta t divided by delta x squared, therefore we can substitute delta t k and delta x squared here to be half multiplied with lambda. Multiply 2 to cancel 1 over 2 here, then you get 2 multiplied with these two terms. Multiply both sides with negative 1, then you obtain negative plus negative. This one is negative plus negative. So on your right hand side you have negative plus after you multiply both sides with negative 1. And don't forget to multiply the lambda inside this equation. So multiply inside, you should get lambda here, 2 lambda, here is negative lambda, here is negative lambda, plus 2 lambda, and then minus lambda. Let's move the TL plus 1 to the left hand side, where you have negative lambda ti plus 1 here, which is this. This term is here, plus 2 lambda ti is this term. And then you have this, when you convert to left hand side, you obtain positive 2 ti, which is this term. So on the right hand side, you have 2 ti, so you have this term, and then you have negative lambda ti plus 1. When you move to the right hand side, you obtain positive ti plus 1, which is this term. So let's move 2 lambda ti to the right hand side, you obtain negative 2 lambda, which is this term. And then for this term, you have negative lambda ti minus 1. When you move to the right side, you obtain positive. So this is the one. So with that, we success to obtain this equation. So this is the numerical modeling result by using the Nicolson method. What we are interested is to find the temperature at point xi at future time index L plus 1. So this is the point where we want to find the temperature, where you have the y-axis to be the time and the x-axis to be your phase x. This is the TIL, the temperature at the point xi at time TL. So this is TL. So the temperature here is L also, I minus 1. And then temperature here is I plus 1 with L. And then you can see these 3 points refer to the temperature here, where the temperature at the current time TL, which is normally known. So we know this in advance. However, in this formula, you have the Ti plus 1, Ti minus 1 at L plus 1. So at time L plus 1 here, so at this point, this is the Ti minus 1 at L plus 1. And this point is the Ti plus 1, L plus 1. So for the temperature at the future time index, normally we don't know. And these are the temperature that we want to determine. So you can see we have 3 unknowns in one equation here. So therefore, to find the unknown, we need to implicitly calculate it by using the matrix method like the previous example. It is worthwhile to mention that you have one additional computational molecule here at TL plus 1 over 2. So what is this? Previously, by using the explicit formula, which is this formula alone, you approximate the d squared T over dx squared by using these 3 temperature information, which is located here, which is at TL. Then you use the implicit method, which is this formula alone, to approximate the d squared T over dx squared by using these 3 temperature information, which is located here at TL plus 1. So when you take the summation of these 2 approximations and divide it by 2, so you actually obtain the d squared T over dx squared information at TL plus 1 over 2. Then you can find the first derivative of the temperature with respect to the time at TL plus 1 over 2 here by using center type of finite difference method, which is second order accurate, where the dt over d time here at TL plus 2 minus with the temperature at the previous time, which is TIL, divide with the 2 time step here, and the time step here is equal to TL plus 1 minus with the TL plus 1 over 2, which is written in this formula. And then you can see that the 2 multiplied with the time step is equal to TL plus 1 minus with TL. Therefore, you can simplify it into this formula. Surprisingly, we find that the previous formula for the first derivative of the temperature is same with this formula, which is developed by using the center finite difference, which is in second order accuracy. It is very important for you to know that for the alternative implicit scheme, or what we call the Crank-Nicolson method, although the formula that we use to approximate the first derivative of temperature is the same with the one when we use explicit method or implicit method. However, explicit and implicit method only have first order accurate, or what we call the OH, because explicit and implicit method are using the forward finite difference method to approximate the first derivative of temperature with respect to time here. On the other hand, the Crank-Nicolson method is using the center finite difference method in order to estimate the same formula, which is second order accurate OH2. In simple, when we use the Nicolson method, we have a better accuracy for the temporal difference approximation because we are using the center finite difference method in order to estimate this. While the explicit and implicit method use the forward type of finite difference method to obtain it. Let's continue to solve the example 4 by using the alternative implicit scheme, which is the Nicolson method. So we have the same example in example 1, 2, 3, where this is the initial condition, this is the boundary condition, and then from the k prime c row, you obtain the k to be this answer, and from the k delta x and delta t, you can obtain the lambda. Substitute the lambda inside the Nicolson formula, then you should obtain this equation, and based on the initial and boundary conditions, this is the temperature at the 6th point. As the delta T is equal to 0.1, then we need to find the temperature at T equal to 0.1. So you can see that the temperature at x0 and the temperature at x5 is equal to 150, follow the boundary condition. And the rest we need to find the temperature at point x1, 2, 3, and 4. To find the T11, let the TIL plus 1 equal to T11 here, and you get I equal to 1, and your L plus 1 equal to 1. Therefore, you obtain your L to be 0. So substitute the I and L inside this formula, and you should be able to obtain this equation here. Then we can substitute the T01 inside here. T11 unknown remain, T21 unknown remain, T00 substitute 100 here, T10 substitute 0 inside, T20 substitute 0 inside here. And then calculate the constant, you should be able to obtain 4.175. So this is the first equation that you obtain. Then we continue to solve the T21. In simple, just replace the previous equation here, T11 to be T21. And then you replace the 0 here, become 1, 1 here become 3. On your right hand side, replace 0 to be 1, 1 to be 2, 2 to be 3. So all of them increase by 1 at the space index. To find the T31, increase the space index again, then you will get this. So for example, 2 here increased by 1, you obtain T31, which is what you want to find here. And then 1 here becomes 2, 3 becomes 4, 1 becomes 2, and so on. So again, to find T41, we increase the space index here. Substitute the T11, T21, T31 here. So since you don't know the value, so we just remain. And then substitute the T10, T20, T30 here. So since all of them is 0, therefore you obtain 0 on your right side. Then we continue, substitute the T21, T31, T41. So since we don't know the answer here, we just remain here. And then T20, we can find it to be 0. T30 and T40 are 0 as well. Therefore, you obtain 0 on your right side. And lastly, you obtain T31 to be unknown, and then T41 to be unknown as well. T51, you know it is equal to 50, so you can substitute inside here. T30 is 0, T40 is 0, and lastly you have T50, 50. So substitute inside here, you should be able to obtain the constant 2.0875. So this is your second equation, third and fourth equation. Then we can convert these four equations into matrix format and solve it using the inverse method, and you should be able to obtain the solution at t equal to 0.1, So you can see that the alternative implicit scheme or the Crank-Nicolson method has the same procedure with the previous implicit method.